Okay, good morning. So I'd like to wrap up our discussion on closed chain kinematics by today looking at, again, we're going to use examples, okay, to start from simple examples and work our way up. And today we're going to look at differential kinematics, okay, essentially the Jacobian. Now there are several types of Jacobian when it comes to closed chains. We'll look at that and use that as a basis to do a singularity analysis of closed chains. Okay, so let's get to work. All right, so last time we looked at some very basic closed chains, right? We looked at the three RPR mechanism. We looked at the Stewart-Goff platform. To give you an indication of how kinematic analysis is done, okay, for closed chains. Usually you end up with a set of equations, okay, and embedded in those equations are both the forward kinematics and the inverse kinematics, okay. So we're going to continue that line of development, and today begin by looking at a slightly more general mechanism, okay, than the ones we looked at before. And I mean general in the sense that we need a more general type of analysis. Okay, so we're going to look at the 3UPU. Okay, but it could in fact be any parallel mechanism. Okay, all right. So let's draw the 3UPU here. So let's draw it. Yeah, all right, let's draw it this way. Oops, that's not right. Okay, then let's draw one right here. Okay, so here's what the structure looks like. Okay, so it consists of three UPU open chains. So here's a U joint, which is really two R joints connected orthogonally, a P joint, and then another U joint. Okay, so we have three of these. So let's first draw some frames. So here's my fixed frame. Here's my tool frame. Okay. So I'm going to call this chain 1, chain 2, and chain 3. Okay. So here's chain 1. Let me call it T1. Chain 2, T2, and chain 3, T3. Okay. All right, so let's label the joints. So this joint we'll call theta 1, theta 2, theta 3, theta 4, theta 5. Okay, so that'll be, we'll say that the joint at the base is theta 1 and work our way up to theta 5. Okay, same thing here. Let's use a different letter. Let's call the joints in chain 2, let's use phi. Okay, so phi 1 would be coming out. Phi 1, here's phi 2. Okay, here is phi 3. Okay, phi 4, phi 5. All right, it's already getting cluttered. Okay, and let's call the joints for chain 3 psi. So here's psi 1, psi 2, psi 3, okay, and so on. Psi 4, psi 5. All right, so we have quite a mess here. Okay. So let's do a kinematic analysis. Okay. All right, so for this type of problem, and this is what I mean by this being a little slightly more general case. Okay. The way we set up the kinematics is as follows. We say that, think of these as 3 open chains. Okay, chain 1, chain 2, chain 3. Okay. Each chain goes to the same end effector. Okay, so we can write T1 of theta is equal to T2 of phi. Okay, so it's basically 2 open chains having the same end effector. Okay, and also T2 of phi equals T3 of psi. Okay. All right, so these represent what? 6 independent equations. Okay. These are, let's call it equation 1, equation 2. Okay, so 1 and 2 each represent 6 independent equations. Okay, and now how many joint variables are there? Let's see, there's theta, phi, and psi. Each are 5-dimensional. So we have 15. Okay, so we have 15 variables. Okay, so a simple counting argument, right? We have 12 equations, 6 plus 6. Okay, 15 variables. So 15 minus 12 gives us 3 degrees of freedom. Okay, so therefore, by simple counting analysis, dimensional analysis, the mechanism has 15 minus 12 equals 3 degrees of freedom. Okay, and this is the kind of analysis that you have to resort to when you have very general mechanisms. Okay, when you have very general parallel mechanisms, you usually want to set it up as a number of open chains, okay, and say that the open chains have the same end effector frame. And then from here, it's a question of how do you reduce this to a set of 6 independent equations, okay? Or the other way is to add more equations, right? For example, if you want to work just in terms of rotation matrices, okay, then you might want to add the constraint, say R transpose R is the identity, okay, in which case that increases the number of equations, okay, but the equations themselves might be simpler in form. Okay, all right, so if possible, you want to try to avoid this, okay? When you look at a mechanism, you want to try to exploit as much as possible, any special features, for example, symmetry, whatever, okay? So the kind of analysis I showed you last time with the 3RPR or the Stewart platform, okay? Usually that's the kind of analysis that people do, okay? To try to make the equations as simple as possible. All right, so remark. Try to exploit any special features of kinematic structure. Okay, so for example, symmetry. Okay, and spherical joints, for example. Turn out when you have spherical joints, the analysis simplifies somewhat. Okay, all right, so that's the, I hope this gives you a flavor of right, analysis of parallel mechanism kinematics in the general case. All right, now let's go to the differential kinematics. Okay, now in the differential kinematics, in the open chain case, remember what this was. In the open chain case, okay, it was basically governed by this equation. Okay, so namely, what is the relation between joint velocities and the end effector velocity? Okay, and it's given by this Jacobian matrix, right? You multiply the joint velocity vector by the Jacobian to get the end effector velocity. Okay, for closed chains, there is this analysis. There's this notion of differential kinematics, but there's another notion of differential kinematics. Okay? So for closed chains, things get a little bit more complicated. Okay? There's this notion, and then there's another notion. Okay? There's more than one Jacobian. Okay, so let me show you what I mean by that. So let's look at the 3UPU mechanism example. Okay, so let's consider the 3UPU. Okay, so we have equation 1. What we can do is we can now take the derivative of both sides of equation 1. Okay, so let's do that. So T1 dot, let's work with right inverses. Okay, so let's say T1 dot T1 inverse is equal to T2 dot T2 inverse. Okay, let's call this equation 3. And similarly, equation 2, we can write T2 dot T2 inverse equals T3 dot T3 inverse. It's equation 4. Okay. All right. So let me erase this street art here. All right. So whatever in there is just the Ford kinematics Jacobian for chain 1 and the Ford kinematics Jacobian for chain 2 and set them equal to each other. Okay, so I could write it in this way. I could say J1 of theta times theta dot is equal to J2 of theta times, actually it's J2 of phi, right? Phi dot. And also J2 of phi dot is J3 of psi times psi dot. Okay. Incidentally, I don't need to write T1 equals T3, right? I wrote T1 equals T2, T2 equals T3, right? So writing T1 equals T3 is redundant. Don't need to do it. Okay, it's already there. Okay, so I can write it this way. All right. Now we saw that it's a 3-degree of freedom mechanism. Okay, so in a closed chain, the degrees of freedom, what? Represents the number of independent joints, okay, 1 degree of freedom joints that can be actuated. Okay, so in this mechanism, 3 joints can be actuated. Okay, usually it's the P joint. Okay, so let's assume it's the prismatic joints that are actuated. Okay, those joints are what? Theta 3, phi 3, and psi 3, right? So these are theta 3, phi 3, and psi 3. Okay. Okay, then the actuated joints, I'm going to use new notation, okay? Notation. Okay, so QA is my vector of actuated joints. It's theta 3, phi 3, psi 3. Okay, so it's three-dimensional. Okay, and the rest of the joints, so how many are left? 12, right? 12 joints. I'm going to use notation QP. Okay, so this consists of, all right, let me write it in row fashion because it's going to get too long. So this will have theta 1, theta 2, theta 4, theta 5. Just drop the actuated joints. Okay, phi 1, phi 2, phi 4, phi 5, and then psi 1, psi 2, psi 4, psi 5. I guess I should transpose this. Okay, so it's 12-dimensional. Okay, so this is going to be my vector of passive joints. So actuated, active, no, not actuated, passive. Okay, so passive joints. Okay, and now if I want to put QA and QP together, I could say this is just QA stacked on top of QP, for example. Okay, so this is my 15-dimensional vector of all joints. All right, let's number these equations. Let's call this 5. Let's call this 6. Okay. Now let me rewrite 5 and 6 in matrix form. Rewrite 5 and 6 as follows. All right, so let me put J1 of theta here, and minus J2 of theta of phi here, 0 here, 0, minus J2 of phi, J3 of psi. Okay, this multiplied by the vector theta dot, phi dot, psi dot. Okay, all this equals 0. Okay, so all I've written is J1 theta dot minus J2 phi dot equals 0. Okay, that's equation 5. And minus J2 phi dot plus J3 psi dot equals 0. That's equation 6. Okay, all right. So I have this single matrix equation. Okay, now here's what I'm going to do. I'm going to now use my new notation. Use my new notation. Use my Q sub A and Q sub P. So replace all the thetas, phis, and psis by the appropriate QAs and QPs. Okay, also here too. And then I'm going to shuffle this around. Bring all the QAs to the top, all the QPs to the bottom. Okay, so now let's call this equation 7. Okay, so now we're going to use new notation. Okay, and rearrange equation number 7. Okay, to get some matrix, okay, times QA dot, QP dot, okay, equals 0. Okay, so let's see what goes here. Well, let's call this part, let's call it H. Use the letter H. So H sub A, okay, and here's H sub P. Okay, All right, so let's think about the dimensions of these things, okay? So QA is 3-dimensional, okay? QP is 12-dimensional. And we have, how many equations here? 12 equations, okay? So this H sub A is what? What's the size of this matrix? It's 12 by 3, I believe. Okay. And H sub P is 12 by 12. It's square. Okay, so when you see square matrices, it's usually a good thing. Okay. All right, let's rewrite this. Okay, so let's rewrite this here. Okay, so this is, I believe, equation 8 now. Okay, so let's write equation 8 as what? It can be written as H sub A QA dot plus H sub P QP dot equals 0. Okay, and now, okay, we make use of the fact that HP is square. So if it's square, means usually a unique inverse can exist, provided it's not singular. Okay, so under that assumption, if HP of Q is non-singular, okay, what can we do? We can solve this equation for Q sub P. Okay, we can write QP dot is equal to minus HP inverse, okay, depends on Q, HA Q times QA dot. All right, so this, okay, so we have this equation here. So what does this say? This says that the velocities at the passive joints, okay, the ones, okay, remember now, the actuated joints, Q sub A, okay, they have motors attached to them. Those are our inputs, okay, so those velocities we control, we provide as inputs. The remaining joints, the passive joints, the velocities can be determined from this equation, okay. All right, so anytime you see an inverse, okay, first thing that should occur to you is, well, what happens if this doesn't exist? What happens if the inverse does not exist? Okay, so it's a kind of a singularity here, okay, but it's a different kind of singularity than the kind we've seen in open chains, because in the open chain case, we're looking at singularities of the forward kinematics Jacobian. Right? So a singularity of an open chain is what? Is when the end effector loses one or more degrees of freedom. Right? In this case, when this becomes singular, we haven't even talked about an end effector, right? So this is a different kind of singularity. We're going to come back to that, but let me just make a remark now. Okay. So if HP is HP sub Q is singular, okay, we have what's called an actuator singularity. Okay, this Q, the value Q at which this HP is singular is called an actuator singularity. Q is an actuator singularity. Okay, so we'll come back to this, so more later. Okay. All right, so let's not worry about the singular case right now. Okay, so let's just write that equation. All right, let's give it a number. So equation 8, this is equation 9. Okay, so let's write equation 9 in the more generic form. So Q sub P is equal to, say, let's use matrix G. So G sub Q times QA dot. Okay, and let's just assume it's not singular, so this exists. All right. Suppose I want to know at what configuration does the end effector lose one or more degrees of freedom? Okay, so it's the same idea as the singularity for open chains. Okay. All right. So suppose I want v, the end effector velocity, spatial velocity, is equal to j sub q times qa dot. Okay, so remember q is the vector of actuated joints. Okay, so v is the end effector spatial velocity. Okay, 6-dimensional. QA dot, remember, is the vector actuated joint velocity vector. So 3-dimensional in our case. I want this. I want this matrix. Let's call it J sub A. Okay, so I want to get this. So when this becomes singular, then it's the same notion as a singularity for open chains, right? Namely, the end effector loses some direction of motion. Okay. All right. So how do we get this? First thing to do, and there are other ways to do this, but pick a chain. Okay. So let's say chain 1. Okay. Say chain 1. Okay. So now let's write down the Jacobian relation for open chain 1. Okay. So we can write this v, spatial velocity. V is equal to J1 of theta, theta dot. Okay. All right, but now, if we write down theta dot, it's 5-dimensional. Okay, 5-dimensional. Which one is actuated? This one. Theta 3 is actuated. And the rest are passive. Theta 1 dot, theta 2 dot, theta 4 dot, theta 5 dot. I don't want this. I only want QA dot appearing here. Okay, so theta 3 dot, phi 3 dot, psi 3 dot. So this is okay. These I don't want. All right. So how do I get rid of these? Well, that's where we use that equation. Okay, so we go over here. this is equation 10, right? If we write out 10, okay, 10 expanded. Okay, we have the passive joints over here. I'm not going to write the whole thing. Let's just write a few. There's theta 1 dot, theta 2 dot, theta 4 dot, theta 5 dot, okay, phi 1 dot, phi 2 dot, so on. Okay, it's going to equal some matrix. Dimension is what? 12 by 3. Right? That matrix G is 12 by 3. So 12 rows, 3 columns. So let me write first row as a row 1, G1 transpose. Okay, so this is row 1. G2 transpose is row 2. Okay, and there are 12 rows. G12 transpose Q. That's the 12th row. Okay, this times QA dot. QA dot, which is theta 3 dot, phi 3 dot, and psi 3 dot. Okay? All right, so I have this. So what I want to replace is these. Okay, so I want to replace these, and I also want to replace these. Okay, so I look at theta 1 dot is this row times these vectors. Aha. So now I can replace this vector theta 1 dot by G1 transpose times this vector QA dot. Okay. I can also do the same for theta 2 dot. Theta 2 dot is G2 transpose times this vector of actuated joints. Okay. So make all the replacements there. Okay. So let me write that down. Okay, so replace theta 1 dot in this equation. So this is equation 11, I guess. Equation 11. Okay. In 11 by the first equation. Theta 1 dot equals G1 transpose Q times, well, this thing, theta 3 dot, phi 3 dot, psi 3 dot. Okay? And similarly for the others. And similarly for, okay, the other remaining 3 joints, theta 2 dot, theta 4 dot, theta 5 dot. Okay, so if you do that, then you get this. Okay? Okay, so replace all that, then you can get finally the result V equals J sub A of Q times QA dot. All right? So it's a lot of work. It's a lot of work. Right? So, and this is what you have to do when you have very general parallel mechanisms, closed chains, that don't have a lot of symmetry or structure that you can exploit. Sometimes this is the only way you can do it. All right? But before giving up, you should always, when you have a new parallel mechanism, okay, see if you can exploit these special features, okay, and try to simplify the equations so that you can hopefully avoid doing this kind of analysis, okay? But when all else fails, at least you'll have this, okay?